In this video, I will show you how you can control 3D printed CyberBrick models with your standard model radio control handset running EdgeTX firmware and having an ESP32 based ExpressLRS radio module. The good news is that no soldering or any other kinds of hardware modifications are needed. You can continue to use the models with existing CyberBrick electronics, and also on the handset side, no hardware changes are needed. Controlling CyberBrick models from an EdgeTX radio equipped with an ExpressLRS module does need firmware modifications though, as we need to explicitly teach the CyberBrick receiver to understand the commands received by an EdgeTX radio and vice versa. All modifications are software-based only, and also everything is reversible in case you wish to undo any step I will show you here in this video. Before we dive into the steps involved, let's get an overview of the involved systems and their interplay. Let's have a look at a typical CyberBrick model, here the popular forklift. All CyberBrick models known to me so far come with the electronics that is made up of two interconnected modules. The two parts are the receiver shield with internal type name X11 and the core module with the type name A11. Let's have a look at each in greater detail. You can attach up to 2 brushed electric motors, up to 4 servos or electronic speed controllers, and up to 8 multicolor LEDs to your X11 receiver shield. The X11 receiver shield is the power distribution and the signal conditioning board and is equipped with electronics to create a smooth 5-volt supply from the battery input for the servos and LEDs. The brushed motor controller amplifies the control signals in a way to be powerful enough to drive the motors. Let's take a look at the CyberBrick core module next. The CyberBrick core module is the brains of the system. It is equipped with an ESP32C3 microcontroller, also performing the radio link communications. The CyberBrick core is equipped with an integrated printed circuit board antenna. It does not have great performance, but fully sufficient for close-range interactions with the models. To control the models, we are going to use a handset that is able to run EdgeTX firmware and either is equipped with an internal ESP32 based ExpressLRS module or has a module bay that supports external ExpressLRS modules. It is crucial that we are using an ESP32 microcontroller based ExpressLRS module in order to talk to CyberBricks, as we are going to switch to ESP-NOW protocol that only works with the microcontrollers from Espressif. ESP-NOW is one possible common denominator that the hardware of both sides support. Nevertheless, the default firmwares of ExpressLRS modules and CyberBrick cores cannot talk to each other, so we need to change that by changing the firmware of both. I have created a new firmware for the ESP32 microcontroller based ExpressLRS modules that is able to output ESP-NOW protocol. The firmware is built and can be flashed using the Visual Studio Code and Platform I/O extension paired with an Arduino framework for Espressif's ESP32 platform, similar to the development of the original ExpressLRS firmware. Also for the CyberBrick side, I have created a custom firmware for its ESP32C3 microcontroller, although the CyberBrick modules are programmed with MicroPython instead. Next, we are going to look in a step-by-step hands-on course on how to download the code, configure and flash it onto both sides. We have 3 mandatory and 1 optional step that we need to go through to control the CyberBrick models from an EdgeTX handset equipped with an ExpressLRS radio module. First, we need to download the project archive from my GitHub project page. In the second step, we will copy my custom MicroPython code to the CyberBrick core module of our model. The third step is optional and only needed if you want the maximum configurability by controlling the LEDs one by one from the EdgeTX handset. And as a last step, we will flash a custom ESP-NOW communication firmware to an ExpressLRS RF module. We're going to start by first downloading the project files from the GitHub. So if you navigate to github.com/rotoman/cyberbrick_ESP-NOW, you'll see the project archive with the receiver files and the transmitter C++ code. So the easiest for anyone without the GitHub account to download would be to press the green Go button and just pick the download zip link, which we're gonna do, and we're gonna save the file now to the desktop. To continue with the receiver flashing, so it's flashing the CyberBrick core module, we are also gonna need Arduino Lab for MicroPython as one example. So you can also use other software if you like Tony, but in this video I'm going to use now Arduino Lab for MicroPython. So you can download this from labs.arduino.cc, in this case in English, /cn/labs/MicroPython. So I'm using Windows here, as this is the majority of users that are using, but you can download for Linux and macOS the same. So I'm going to pick now Windows because I'm on Windows on this computer. And I'm going to save this file on the desktop as well. So you can save anywhere you want. You don't have to save at desktop. And as a third program, we're going to also need the Visual Studio Code. So while I already have the browser open, I'm going to download this as well. So again, in my case, I'm going to download for Windows, but this is available for Mac OS and Linux the same way. So again, I'm going to put the executable onto the desktop. And after the downloads are complete, I can close the browser. As a next step, I'm going to unpack the two zip files that we downloaded in a previous step. I'm going to unpack them to current user documents folder. And after unpacking, I can delete the zip file. So while unpacking Arduino Lab for MicroPython, I see that it extracted as another zip file. So I need to unpack it once more. And also here I can clean up by removing the unnecessary folders and zip files. Let's start next the Arduino Lab for MicroPython by opening the folder and double-clicking on the Arduino Lab for MicroPython executable. On first start, we are asked to enter a folder where the software can store its files, but at the same time, this is also the folder where it fetches the files. So we are gonna give the folder where we unpack the GitHub repository receiver MicroPython files. So we're gonna just click on anywhere on this white window and navigate to the GitHub project receiver py folder and enter that. Let's attach our CyberBrick receiver core module to the computer via USB. I'll maximize the window as well, and let's hit connect button. So you should also see that ESP32C module was detected. If not, you need to check the USB connection. Let's open the files view by clicking the icon on the upper right corner. The files view is used to copy files between your computer and the CyberBrick core module. On the left pane, you see the contents of the CyberBrick core module currently connected. And on the right pane, you see the files on your computer. I have created two types of CyberBrick receiver MicroPython codes, generic and model-specific. The model-specific codes only need main control inputs and control the LED lights from these inputs accordingly. For example, when driving backwards, it turns on reverse lights, or when turning, it blinks automatically, and so on. On the other hand, the generic code allows you to fully control the LEDs from your EdgeTX handset. The generic RGB uses a channel for each of the base colors for each of the maximum possible 8 LEDs, meaning 24 channels are used to control the LEDs. So whereas the hue saturation value based control uses 16 channels to control the hue and value, where saturation is set to full always. In addition, there is also a debug receiver MicroPython code that prints out the received channel values in a terminal when connected to an EdgeTX handset. For demonstration purposes, let's pick to flash the forklift example. But before we copy the forklift code over, let's back up the factory boot file from the CyberBrick to the computer, as in the next step we are going to override it with my custom version. This way you will have an easy backup in case you wish to ever restore the factory state. Bambu Lab offers also on their web page a factory recovery tool, which would also work for this purpose. So to back up the CyberBrick boot file, select it on the left pane and then click the arrow to the right between the panes. Now, after we have backed up the boot file, let's open the forklift folder by double-clicking on it. Let's select both files by holding down the Control key and copy them over to our CyberBrick core by clicking the left arrow key in the middle of the panes. We need to accept to overwrite the boot file here. And it is normal that copying takes some seconds, so I'm going to speed up the video for you here. So after the copying finishes, let's change back into editor view. Next, disconnect physically the USB connection between your computer and your CyberBrick module so that the power is turned off by the CyberBrick module. Just pressing reset will not work here for the first time. After some seconds being powered off, reconnect the CyberBrick core back to your computer via USB. After you hear the audio sound that the USB has been connected, press the connect button in Arduino Lab for MicroPython. And after the terminal opens, press the reset button. And if you did everything correctly, you should now see the MAC address of your receiver being printed in the terminal. Make note of this MAC address because we are going to need this in a later step when flashing the ExpressLRS modules. Although now we already have a working CyberBrick receiver module, optionally we can alter the radio frequency that the ESP-NOW communication will use. ESP-NOW and Wi-Fi share the same spectrum and channel allocation. By default, I have coded the ESP-NOW code to use channel 1, but in case you wish to change that, for example, not to collide with your own or your neighbor's Wi-Fi network, I will herewith show you how you can achieve this. So let's switch back into the files view and select the forklift MicroPython file on the left pane. So it is important that you select it on the CyberBrick module side on the left, as otherwise you would in the next step only alter the file on your computer. So after selecting the forklift.py on the left, let's click the edit button, which is the topmost button between the panes. Next, let's scroll down a bit, in this case to line 51. As an example, I'm going to change here to use channel 11 instead of 1. So I type in 11 and press save. It will take some seconds to save the file. Do note that although for normal 2.4 GHz Wi-Fi there are 13 channels available, the ESP-NOW code seems to only accept values from 1 to 11, so do not try to enter 12 or 13 here. So to double check that the code still starts okay, let's press reset to restart the MicroPython environment on the CyberBrick core. So if you are greeted once more with the MAC address, you should be good to go. This concludes the first part, flashing the CyberBrick modules. You can press disconnect and physically disconnect the CyberBrick core from your computer. You can now attach the flashed CyberBrick core to your receiver shield and assemble it in your model, in this example then into the forklift. Let's see next how to continue with flashing the handset. If your radio control handset is running a recent version of EdgeTX and you do not wish to control the LEDs by yourself using the generic RGB or generic hue saturation value scripts, you can skip this step updating your EdgeTX firmware. If, on the other hand, you do wish to use the generic receiver scripts with highly customizable LED control, then we need to flash a special EdgeTX firmware to your radio. The reason is that the stock CRSF protocol that is used by the system to communicate between the handset microcontroller and the radio module microcontroller can only transport up to 16 channels. With the update I created, you can double it to 32 channels, which is needed to transport the sheer amount of channel data needed to control the maximum amount of LEDs attached to the CyberBrick receiver directly from the handset. As long as the pull request to update the CRSF specification for a 32 channel transport is not merged, also the second pull request implementing this feature to EdgeTX firmware will also be on hold. So we will have for now to use my EdgeTX fork to download the customized EdgeTX firmware. On my GitHub page, I am offering a special EdgeTX Jolimon version 2.11.3 release that adds support for 32 channels with CRSF. The only minor modification of it is to enable the support for the 32 channel transport for CRSF. So let's fetch that firmware package from github.com/rotoman/edgetx/releases. So let's open the assets and next download the file. I will once more save the file onto the desktop. Next, let's unpack the zip file once more into our user documents folder. And after unzipping, we can once more delete the original zip file as we do not need that anymore. If you are on Windows, like I am here on the presentation computer, we do need to first install the direct firmware update drivers, or short called DFU drivers. ST Microelectronics, the original manufacturer of the STM32 microcontroller in the EdgeTX radios, does unfortunately not offer DFU drivers as a separate download, but only as a part of the STM32Cube programmer software package. And this is thus what we need to download next. But it is more difficult than, in my opinion, it has to be, as to be able to download from ST Microelectronics website, we have to make an account at ST and log in. So let's navigate to st.com/en/development-tools/stm32cubeproc.html and let's get the software and get in my case the 64-bit Windows download package, and let's download it once more onto the desktop. I have already made an account and I'm already logged in, but do not wonder if you might be asked next to log in instead. So after the download completes, we can close the web browser. So let's unpack the zip file. And then start the installer. You can just accept the defaults of the installation, as these will be fully sufficient for our purpose. So just keep pressing next and accept all the dialogues that you are presented, and be sure to install also the drivers when asked, and you should be good to go. We navigate to body.edgetx.org and let's open the local file tab. Next, let's click on the big gray box to select the firmware file and navigate to the folder where we extracted our EdgeTX firmware binaries. So for demonstration purposes, I'm gonna flash here the Jumper T15 radio, so we'll pick that. But you naturally need to pick here the radio that you have. I will attach the radio in DFU mode via USB cable to the computer next. The process differs a bit from radio to radio. On some radios you just attach the USB cable while the radio is powered off. On Jumper T15 I have to hold down the boot button while attaching the USB cable while the radio is off. EdgeTX user manual lists methods for various supported radios, and I will put a link here for you to look it up. But let's now get back to flashing our radio. So after the radio has been attached via USB to the computer, we can hit the flash via USB button. So we have to add a new device, and if you did everything correctly, you should have a STM32 bootloader listed that you need to select and hit connect. So after that, we just hit next and we hit start flashing and wait for the flashing to end. So I'll speed up the video here so you don't have to wait. After the flashing is complete, we can click Done and disconnect the USB cable from the radio. To verify that the radio still works, we can power it up and we should be greeted with the normal EdgeTX startup sound.
Welcome to EdgeTX.
That concludes the flashing step. The last task before we can finally control CyberBrick models from an EdgeTX radio is to flash the ExpressLRS module with my custom ESP-NOW talking firmware. But before we can start flashing, we need to once more carry out some preparatory steps. If you followed the steps until here from the beginning, we already downloaded the Visual Studio Code installer, so let's execute it. We need to accept the agreement. Let's click Next. We are going to install into the local user folder, so we do not need administrative privileges. So just click Next, and we accept also the default Start menu folder. All the default settings that are presented are fine, so we accept them and click Next. And we click Install. And we do not launch Visual Studio Code at this point, so I'm gonna uncheck the box and click Finish. Depending on which ExpressLRS module you plan to flash and which operating system you are running on your computer, you might also need to install some virtual serial port drivers. If you plan to flash an ExpressLRS module built into your radio, you are going to need to install STM32 virtual serial port drivers. If, on the other hand, you wish to flash an external ExpressLRS module, then which driver is needed depends on the module hardware, more specifically which chip is built into it. More info about this can be found at the ExpressLRS webpage at expresslrs.org, and then clicking Quick Start and navigating to Updating Transmitters. Here you need to open and read the section about your specific transmitter side module to find out which driver you need. As I am going to flash here for demonstration purposes an internal module, I am going to download and install STM32 virtual port drivers for Windows next. I will overlay the URL to navigate to onto the screen. Ignore the web page saying that these drivers are only for users with Windows operating systems up to Windows 8. It is needed and also works with Windows 10 and Windows 11. Once more, you need to be logged into SD website in order to be able to download the driver. Let's save the file again once on the desktop, and unzip and install it. In case you are running Windows 10 or Windows 11, then just pick the Windows 8 driver appropriate to your system. So in my case, I'm running Windows 11 64-bit, so I'll pick the Windows 8 64-bit install. So we need to enter a company name. In this case, I have none, so we just enter private, and we can accept the default location to install, and we have to install the driver. We do not need to check program updates as we just downloaded the file, so we can skip this step and we are done. We can clean our desktop by deleting the unnecessary installation files. To flash our transmitter side ExpressLRS module with the custom ESP-NOW code, let's first start Visual Studio Code. As a first step, we need to install Platform I/O extension for Visual Studio Code. For this, let's click on the extension button on the left Windows side and enter Platform I/O into the search bar. Let's click Install to install Platform I/O IDE. We trust the publisher and allow the installation. Be patient, as this can take, even on a new computer and good internet connection, many minutes to complete. After the Platform I/O installer has finished, we need to restart Visual Studio Code. So just close the window and reopen it. Let's now click the new Platform I/O button on the left pane, and let's click Pick a Folder, where we navigate to our downloaded GitHub transmitter side code and open this. First time opening the project, prepare for a long wait, as Platform I/O needs to download a lot of data and unpack it, so it takes many minutes for this to finish. You need to be patient, do not cancel the process, otherwise you need to start from the beginning. Phew, that took 12 minutes and 40 seconds on my computer. So just be patient and wait until the process finishes. Remember that we saved our CyberBrick core module MAC address in an earlier step. Now we are going to embed that address into our transmitter side code. For this, let's unfold the source folder and open via double-clicking the main C++ file. So after the initial comments, we will find the definition for CyberBrick receiver MAC addresses. You will see 3 placeholders for 3 models. You can only use a single line, or you can use up to 64 lines to define 64 CyberBrick models. I will add here directly my 5 CyberBrick model addresses that I have previously gathered using the process I showed earlier. This way you can use your single radio to control up to 64 CyberBrick models. Remember that we changed our Wi-Fi channel from default 1 to 11 previously, so we need to match the channel info also on the transmitter side. So after carrying out the changes, save the file. We can next prepare to build and flash the code onto our handset's radio module. Let's open the Platform I/O submenu by clicking the Platform I/O icon on the left sidebar. Under the project tasks, you will see a list of currently supported internal and external ExpressLRS modules. As we are flashing Radio Master MT12 in this example, we need to scroll down a bit. As a first step, let's open the Radio Master MT12 folder by clicking on it. So now it is crucial that after you click to open the folder for the first time, you first give Platform I/O some time to do its needed processing and do not click anywhere else. Somewhat weirdly, after Platform I/O finishes the preparations, it closes the opened menu item and returns back to the beginning of the list. Now comes the next crucial point. We need to click that exact menu item that we clicked previously once more, and be sure not to click any other item on the menu. So if we did everything correctly, we are now greeted with a number of options where upload is one of them. But before we can hit that button, we need to first prepare and attach our radio to the computer. So let's have a look next how to proceed with this. Let's first check that the settings under EdgeTX for internal ExpressLRS module and pass-through flashing are correctly set. For this, let's power up the radio.
Welcome to EdgeTX.
Then let's navigate to System and to Hardware page. And let's scroll down to Internal module. The type is already correctly set to CRSF. You can pick any baud rate that the radio supports, so here 921K is perfectly fine. Next, let's check that the USB virtual communication port is set to CLI. And this is also the case. The latter is necessary to be able to flash the internal ExpressLRS module through EdgeTX. We are good to go, so let's attach USB cable. For pass-through flashing of internal ExpressLRS module, we need to pick USB serial. After the radio is connected to the computer via USB in serial pass-through mode, we can hit that upload button. Once more, give Visual Studio Code and Platform I/O time to build the code and flash it onto the handset radio module. If all went well, you should see a green success on your screen. After flashing has completed, we can disconnect the USB cable. Let's power cycle the radio next.
Welcome to EdgeTX.
So let's open the model settings and let's turn on the internal RF module. Some steps back, we entered multiple model MAC addresses into the code. Using the receiver number here, we can pick the model which we want to control. In my case, I had the forklift under position 1, so let's pick 1 here. To learn what input channels the MicroPython receiver code expects, let's examine its code with a text editor. I will open the forklift code here directly in GitHub. In each MicroPython example I have made, you will find the info in the header of the file. In case of forklift, channel 6 is used to control the fork and mix between channel 1 for steering and channel 3 for throttle drives the tracks. If you are new to EdgeTX, there are lots of material available on the internet. If you are more a reader type, have a look at the official EdgeTX user manual. On the other hand, if you prefer to watch videos instead, then there are a large number of content creators publishing fabulous learning materials. I have here put up a short list of some of the really good content creators that I can recommend without hesitation. There you have it. Now you can use your normal radio handset to control CyberBrick models with all the benefits and features that EdgeTX offers. If you want to see the system in action, come and visit us at EdgeTX Fest 2025. This year's fest takes place mid-October in Brisbane, Australia. Hope to see you there.